take up this the general organic chemistry today. In this, the topic 1 is bonding in the carbon compounds. Bonding means, for example, you have a ethane molecule and there is another ethane molecule. So, we have to take up the two issues here. One is how this ethane molecule is constructed, what types of bonds are there between the carbon and hydrogen with carbon, what type of electrons are used to make this bond and all that. This comes under the hybridization topic. So, therefore, there is a subtopic A is called hybridization. There is another aspect that if this ethane molecule come to closer to the another ethane molecule, is there any forces in between these two? That also matters in the their physical properties like boiling points and all that. Therefore, we are also taking that aspect under this the bonding in the carbon compounds under the name intermolecular forces. Intermolecular forces like hydrogen bonding and the van der Waals forces and the dipole attractions and so on. We will discuss whether they are present or not. If they are present, to what extent they are going to influence their physical and chemical properties, we will discuss. So, let us take the first topic, hybridization. So, the carbon is observed to show 3 different types of the hybridization. The first one is sp3 hybridization. sp3 hybridization. A simple example is a carbon when it is having bonds with the 4 hydrogens, the molecule is known as methane. This is the simplest example to explain this sp3 hybridization. So, the carbon has 6 electrons. These 6 electrons are arranged in the 1s2, 2s2, 2p2 electronic configuration. However, if you carefully observe, the s2 electrons are paired up, whereas p x, y, z, only 2 electrons are having this unpaired situation. In general, it is observed that the unpaired electrons are going to pair up and then develops a bond formation with the neighboring atoms. So, as per that, so only 2 electrons are available. So, therefore, we expect the 2 bonds, but already example we have taken is showing the 4 bonds. Then how do you explain? Means this is not the electronic configuration. Consider this as a ground state electronic configuration with the available energy, some energy it is observing, and then it is undergoing excitation wherein 1s2 will be intact, but the 1 s electron from s orbital to p orbital jumping, we call it as a excitation. So, s orbital will have 1 electron. In the 2 also you can demark like 2p x1, 2p y1, 2p z1. So, now the 4 electrons are there to answer this 4 bonds formation, that is called tetravalency. So, we are now able to explain how the carbon makes tetravalency in spite of having only 2 available unpaired electrons. Means we have to propose this promotion rule or excitation principle, wherein the ground state has converted into excited state in which 4 electrons are available. But we have another problem. What is that? One orbital is its shape is round, spherical shape, and it can make the bond from any direction, that is called non-directional property. Whereas px, py, pz are dumbbell shapes and they are specifically designed in the x and y and z axis oriented. They are axis oriented, so therefore any atom comes in that axis, they can make the bond, otherwise the collision will become waste. So 3 are directional, 1 is non-directional, but it is observed in the methane molecule all the 4 are directional only. How this identical type of properties which are not exactly there in the before bond formation has come means we are proposing a theory called what? Hybridization. In the hybridization we have a set rules are there. However, as simplified here, the first rule is the number of anhybrid orbitals involved in the hybridization. The same number of orbitals are produced, that is 1 plus 3, 4 hybrid orbitals are produced. They will have both the qualities S and P, not exactly in the same ratio and all that, but some of the advantageous qualities, like the first one has a non-directional property, the other 3 are directional, but when all are mixed, only directional quality has prevailed, non-directional quality has disappeared. Like that, some of the advantageous qualities are coming to the orbitals, which is now called as a hybrid. Just like a hybrid, plants will have advantageous qualities in an extra quality, and at the cost of unwanted qualities they are emerged. Like this here also, the hybrid orbitals have got some special features. The orbital shapes are designed, or they have a quality of more overlapping capacity in order to get the stronger bonds. The hybrid orbital shape is neither the dumbbell nor the spherical. You can define as spherically dumbbell. How many are means 4. All these 4 are now directional. With reference to the central point, if one you write like this, the other 3 you write opposite to the first one. So all the orbitals will be equally sized, and 4 sides 4 will be the fixed. They are rigid in their symmetry, having the same type of the bond angles in between any 2 orbitals. If you see, the angle will be the same. So that is the particular shape is described as what? Tetrahedral shape. In fact, the theory shows that if only 2 hybrid orbitals are formed, just let us say S and P, sp, 2 hybrid orbitals, in order to have the maximum this angle separation, they will have a linear shape. Only S and P, for example, S and P are fixed and undergone hybridization. 2 sp orbitals are formed, making a linear shape, having the 180 degrees angle. If S and 2P are involved, then 3 sides 3 will be there. That will be the sp2 hybridization with a 120 degree separation with a trigonal planar. If 4 are there, 4 sides 4 having the equal bond angles, or the separation of the orbitals will be, now the angle separation will be 109 degrees 28 minutes. These 4 hybrid orbitals now are going to overlap with the 4 hydrogens, which are said to be 1s1 orbitals they are having. So therefore their shape will be spherical, and you can draw a molecule like sp3 orbital of the carbon with the s orbital of the hydrogen, like that 4 sides 4 equally overlapping. So this is the molecule of the methane. The central carbon will be having the 4 hybrid, that is 4 identical orbitals. The process of mixing different atomic orbitals, giving rise to the same number of hybrid orbitals having the same nearly energetic, but they have a one special quality: they can overlap more extent, leaving the small lobe. The entire big spherical lobe will overlap. Therefore, the percentage of overlapping will be more, so the bond formation will be strong enough. All such strong bonds are designed by name the sigma. So there are 4 sigma bonds are formed, and inevitably that hybrid orbitals or sigma bonds are stronger bonds, or vice versa is true, all strong bonds we call as a sigma bonds. Now, when ethane molecule coming, how do you explain? Means one sp3 orbital of the first carbon, another sp3 orbital of the second carbon will make a sigma bond formation, and then there will be three another hybrid orbitals at the carbon 1 making the overlapping with the hydrogens, another three hydrogen orbitals at the second carbon also overlap with the hydrogens making the three more sigma bonds, and net is between the carbon and carbon 1 sigma bond, and with three hydrogens this side 3 sigma, that side 3 sigma, total 7 sigma bonds are existing in the ethane molecule. Now, the symmetry of if methane alone is discussed, this is perfectly tetrahedron, but the symmetry of the ethane is pertaining to this particular part is tetrahedral. Again another tetrahedral is there, one encroaching into another one. Entire molecule is not tetrahedral. The symmetry at this carbon 1 is tetrahedral, carbon 2 is also tetrahedral. There are two tetrahedrons, individual tetrahedrons are there, one encroaching into the other one because the bond overlapping results in a bond formation. So, therefore, one tetrahedron encroached, there are two tetrahedrons are there, they are not totally separated, they are encroached one into the other one. That is the exactly symmetry of the ethane molecule. Now, let us go for the second type of the hybridization, sp2 hybridization. This is. So, in this hybridization the best example and the simple one is a ethylene molecule, that is 2 carbons and 4 hydrogens with a in between the 2 carbons 2 bonds are 1 sigma 1 pi bond is an example for the sp2 hybridization. This is called ethene molecule. And now this the hybridization will be in the excited state as we have proposed. 1s 2 will be as it is, but 2s1 2px1 2py1 2pz1, out of these 4 only the s and 2p orbitals are undergoing hybridization, resulting in the 3 hybrid orbitals, namely sp2 1s 2p representing. So, therefore, we call them as a 3 sp2 orbitals, and this pz orbitals will be as it is a unhybrid orbital will be there, and these 3 will be small lobe and a big lobe. 3 will be identical having the equally separated. So, therefore, angle of separation will be 120 degrees. They make a trigonal and a planar. All 3 will touch the ground if you place on a table, and with reference to this plane the pz orbital, which is a dumbbell shape orbital, little cylindrical, and because it is not mixed up with s orbital, a long shape will be there, however one unpaired electron. All these 3 also will have the 1 unpaired, but they are hybrid orbitals, and this is unhybrid orbital. 2 that is the dumbbell shaped lobes will be there. In that lobe 1 electron is existing. Now, if this is allowed with the to make the ethylene molecule, 2 such carbons you have to propose. So, therefore, the carbon 1 having the 1 sp2 orbital, carbon 2 is having another sp2 orbital, a sigma bond is formed, and here there is one pz orbital which is making the pi bond formation. This is out of the pz orbital versus pz of the another carbon. Here we have 2 hybrid orbitals which are overlapping with the hydrogens, and here also 2 sp2 orbitals with the hydrogens. So, totally 4 sigma bonds with the 4 hydrogens, 1 sigma between the carbon 1 and carbon 2. Another extra bond. This bond is resulting by the not by the end on overlapping, the orbitals are parallel to each other, strictly speaking they cannot overlap, but because they are flexible clouds, so slowly out of the attraction they bend together and then have a sidewise or a small overlapping, lateral overlapping, resulting a weak bond. We call it as a pi bond. So a sigma bond and pi bond together we call it as a double bond formation. However, the pi bond is not coming into the discussion of the bond angles. The bond angles strictly based on the hybrid orbitals. sp2 hybrid orbitals will have a 120 degrees, so therefore the bond angles present in ethylene also 120. Here in this case the symmetry of the ethylene molecule can be said as, at the carbon 1 we have a trigonal planarity, carbon 2 also trigonal planarity, but the two trigones will come into the same plane in order to overlap this PZ and PZ. They will come parallel, means the planes of the first trigonal planar, second trigonal planar also will be in the same plane. So therefore the entire molecule, that is 2 carbons and 6 hydrogens, if you throw on the table they touch the ground. So you can say individual carbon is having trigonal planarity, but the entire molecule is having planar molecule. So the symmetry of ethene or ethylene molecule is planar. Don't say trigonal planar, means restricting to the only one carbon. Entire molecule, if you want to say, it is a planar molecule. So as long as the carbons are sp2, the molecule may be little bigger, but the entire molecule will come into the same plane. So therefore this particular molecule is also a planar. On the whole it is a planar molecule having 1 sigma 1 pi between the carbon 1 and the carbon 2, called double bond formation. Now let us go for the another third type of the hybridization, that is under the third type is sp hybridization. This we find is an example. See, triple bond with the carbon and 1 hydrogen that side, 1 hydrogen this side. Systematically it is called ethine, or commonly known as acetylene. Acetylene is the common name, ethine is the systematic or IUPAC name. All carbons are 2 carbon, 2 carbon, 2. Ethane, ethene, ethine. Triple bond is referred as a ine. So therefore it is systematically called ethine. Now in this case the carbon is making 1 sigma bond with that side. As I said, out of the triple bond only 1 is sigma bond, as we have seen in the double bond. So 2 sigma bonds means 2 are hybridized. So let us go for the excited state electronic configuration. 1s2, 2s1, 2px1, 2py1, 2pz1. Out of these 4 electrons, only 2 undergoes hybridization. Hybridization is mixing. So p has no meaning of mixing. So inevitably S and P will be mixed, and the spherical and the dumbbell are mixed, so that spherically dumbbell orbitals 2 are formed. The 2 orbitals will be, each one will be opposing the other one, so that the maximum separation, that is 180 degrees. The more the separation, less will be the inter-repulsion, that is orbital repulsion. Less the repulsion, more stability. So therefore hybrid orbitals will have this particular rule. All hybrid orbitals will orient in such a way the repulsion will be less, or the maximum the separation. So the maximum separation between 2 hybrid orbitals is 180, having a shape of line shape or linear shape. Now with reference to this x-axis line, the y and z, this is the y-axis. On this y-axis there is one py orbital, that is without hybridized 1 electron, and another py will be just like this, half orbital towards us, half orbital will be backside. But however we cannot draw that, therefore we write an imaginary line, that is the z-axis. On the z-axis half orbital this side and half orbital that side, that is these 2 are unhybrid orbitals and these two are hybrid orbitals. Now, to make a molecule of acetylene, you have to take the two sp hybridized the carbon atoms and show this the molecule formation. So, let us write that acetylene, how it is acetylene formed means. So, let us take one hybrid orbital sp2 of carbon 1, hybrid orbital of the another sp2 of the sp hybridized orbital. Sorry, these two are sp hybridized orbital. So, each sp hybrid orbital making a sigma bond, another sp orbital is allowed to make the hydrogen bonding. So, both at carbon 1 and carbon 2 hybrid orbitals are exhausted because of the sigma bond in the center and sigma bond this side with hydrogen, that side with hydrogen. Now, the leftover py will have a lateral overlapping. Actually, the orbitals will come close slowly and bent like this, undergo hybridization, overlapping. But we cannot write disturbing the already the figure drawn. So, we write one or two lines that shows the attraction developing and they are going to make another bond formation or a weak bond, it is called pi bond. Now, there are two more hybrid orbitals like this, these are called pz orbitals, will have another overlapping in front of the this side back front side and the back side of the board, or you draw these orbitals like this. So, that these two also overlap, another sidewise overlapping making the another pi bond. So, there is one sigma bond and there are two pi bonds in between the carbon 1 and carbon 2, that makes a triple bond formation or this ethine molecule formation with one hydrogen that side and this side. Now, the leaving the this pi bonds shapes and all that, leave it. The sigma bonds, the molecule core structure is sigma bonds. So, between the carbon and hydrogen, all the four atoms lie on the same line. So, the symmetry of this molecule is said to be line shape or linear shape, right. So, the orbitals, hybrid orbitals separation is the molecular bond angles also here is 180. So, therefore, at the two carbons, both the carbons 180 the bond angles are there. So, this is all about the sp hybridization. We have taken a molecule like ethine. However, now the different types of the questions, like for example, let us make all this what we have studied in one chart form, so that we can memorize or remember for the longer time. The chart 1 shows that how many sigma bonds whenever carbon makes what type of hybridization. The chart 1 referring that whenever carbon makes 4 sigma bonds, it is nothing but the sp3 hybridization. When carbon makes 3 sigma bonds, it is nothing but the sp2 hybridization. When carbon makes 2 sigma bonds, it is sp hybridization, we can guess. But however, we have some exceptions and all that we will see later. Similarly, which bonds are sigma, to identify that all the carbon hydrogens and the carbon nitrogen, carbon halogen and so on, all this oxygen, also all these are all nothing but the sigma bonds only. Whenever a double bond comes between carbon nitrogen or carbon oxygen and so on, they are 1 sigma plus 1 pi bonds, right. Whenever a triple bond is there like carbon or carbon nitrogen, we have 1 sigma bond plus 2 pi bonds. That means, when a multiple bonds are coming, one will be inevitably sigma bond will be there, that is the strong bond. In addition to that strong bond, extra bonds we are considering as a pi bonds. So, first of all, the molecule, if it is given, search or identify what types of bonds that middle carbon, that central carbon or the middle carbon it is making. Are they sigma bonds or combination of sigma and 1 pi or sigma and 2 pi? Total how many bonds the carbon making, first identify. Then come to this the understanding what number of sigma bonds it is making. 4 hybrid orbitals it is making means that is s and 3 p orbitals combination only gives 4 hybrid orbital, that must be sp3. 3 sigma bonds it is making means that is s1 and x1 px1 py1 making, and another one is going for the pi bond. So, therefore, 3 undergoing hybridization means sp2. Similarly, 1s leave it, 2s1 2px1 if it undergoes 2 sigma bonds are coming, that is sp hybridization. You too can take another type of the chart wherein you can take the different hybridizations versus example ethane molecule, ethylene molecule and acetylene molecule. This has got 3 hydrogens, this is 2 hydrogens, and this is a 1 hydrogen. And number of sigma bonds already we have identified. The carbon is with 3 hydrogens 1 sigma, so 4 sigma, that is what the example for the sp3 hybridization. And the symmetry at each carbon is described as tetrahedral, and this is trigonal planar. This is a linear symmetry, and the bond angles, this is 109 degrees 28 minutes, 120 degrees trigonal planar, linear will have a 180 degrees, right. This you can extend further, like the carbon-carbon bond length. In ethane it is 1.54 angstrom units, in ethylene 1.34 angstrom units, this is around 1.2 angstrom units. Here one thing we can observe that as the hybridization is changing from ethane to acetylene, the bond length is decreasing. This may be questioned, why the bond length is decreasing between the carbon and carbon. There are 2 answers. One is number of bonds increase. Each bond is an attraction force. So, as the number of bonds increases, the bond length is gradually very small, but gradually decreasing. Second one is the carbon of a hybridized nature, as the percentage changes. Let us say an example, if the S character is and the P character, if you show as a symbolically, if S character is 0, P character is 100, then the orbital shape will be definitely, it is 100% P orbital. Equally lobes are there, isn't it? So, exactly the dumbbell will be there. If the S character is 100%, is S is 100 and the P is 0, then the shape of this hybrid orbital will be perfectly spherical. S will be spherical, isn't it? P is not there, only S. Now, these 3 will have in between percentages, like S character is 25% and P character 75, and this orbital is small s has come now, P orbital is also there. As the S character has becoming to 33 and the P character 66, the S character much more isn't it, increasing. S means that the spherical shape is going on increasing. If the S character is 50 and 50, this is 100 and 0, then this orbital will be very small, slope will be there, big P character will be there. To precisely, if you show, this will be like this. So, what's happening is as the S character is increasing, spherical nature is increasing. This is sp hybrid orbital. So, sp hybrid orbital, the wasting part will be decreasing, and the spherical nature is increasing, therefore overlapping nature will be increases, bond length decreases and it will become strong enough. As the S character is increasing, the shape of the hybrid orbital is differing. So therefore, in the first bond formed itself, it is a short bond because the orbital is short. So the bond formed between the C and C itself is a short bond. Because of that, it is using the sp hybrid orbital it is using. So the bond itself, the sigma bonds, only sigma bonds if you measure also it will be like this. This is also influencing in the, for example, if you see the acetylene CH and ethylene CH and ethane CH, all are after all CH bonds only, but the bond lengths are not exactly same. This is around 1.11 or 1.01, 1.0. So gradual decrease is there from sp3 carbon hydrogen to sp carbon hydrogen bond length. Very small decreasing, but it is accountable. On account of what we are explaining means the hybrid orbital used is something different when compared with the sp3 hybrid orbital. It is short one, overlaps more the S character. So electronegativity also will be more, slightly more overlapping means more pulling. So therefore, as a result, the stronger bond will be formed and the length of the hybrid orbital decreasing, therefore the CH bonds also decrease. It is also specifically observed that the nature of the molecules also, in ethane the electrons are neutrally spread over, therefore you find a neutral nature, but here it is basic in nature and here it is slightly acidic in nature. How this acidity is explained? Okay, from the neutral you explain the orbitals are equally shared, there is no accumulation nor deficiency of electrons. So alkanes are perfectly neutral. Alkenes have a loose bond, so that means electron availability is there here and there, wherever the pi bond is there, electron availability is there, one can break the pi bond and get the electrons, means they are source for the electron, therefore ethylene is explained to be basic or Lewis base it is. Whereas acetylene is expected to be more basic because 2 pi bonds are there, but contrarily what we are observing is it is acidic because this side the pi electrons are having the more S character, therefore they are more overlapped or the more S character involving carbons are involved, therefore pi bond also the nature of cloud will be shrinken and the cloud appears to be little smaller and they are closer to the carbon, they are packed type in fact. And the CH bond is also, the bond is strong, however the carbon pulls too much and then it undergoes heterolytic fission leading to give acetylide anion and the proton. So all the proton donors are nothing but the acids. So therefore we explain the acidity of this acetylene molecule based on this type of the concept, that is, as the carbon increases S percentage from sp3 to sp2, the sigma bond of the CH has become more and more strong, however, but a time has come it undergoes heterolytic fission because of the more pulling of the carbon, leaving the hydrogen without electron, that is proton is given out. So acetylene shows acidic property. However, the alkynes having no such hydrogen, let us say an example 2-butene is no more acidic because there is no hydrogen attached to sp carbon. Moreover, triple bond shows some basic character. So therefore 2-butene is basic but not acidic at all. The same type of the butane, when you have a triple bond and the last carbon hydrogen is there, this hydrogen causes the acidity. So it is not the just hydrogen, but the hydrogen should be attached to sp hybridized carbon, then only the carbon pulls electrons and undergoes a heterolytic fission, leaving the carbon as a hydrogen as a proton, and the proton donors are therefore observed as acidic nature. So acetylene and all alkynes containing triple bond on the one of the end, they are termed as one alkynes, or terminal alkynes are acidic, but alkynes having triple bond in the center, middle triple bonded compounds are no more acidic, they are in fact slight basic, but weaker bases than the ethylene. So, this is all hybridization and its concepts, that is consequences on the molecules. Now, the hybridization not only in the molecules, but the hybridization of the intermediate species like charged species and free radicals also let us examine. One such a the hybridization is in the CH3 plus. This is a carbocation, and the smallest one is that CH3 plus. Now, its excited state electronic configuration is 1s2, 2s1, 2px1, 2py1, 2pz1, right. Now, one theory is 3 sigma bonds it is making, therefore sp2 hybridization, that is also right. But let us see what happened on this situation. This is the neutral carbon having the excited state. Here one electron it is lost, that is from methane molecule. Imagine that one hydrogen is removed, with 2 electrons it is gone out. So, what is left over is CH3 with no electron of its own. So, that is why CH3 plus, that means one electron is removed. So, you will have a 2s1, 2px1 and 2py1, 2pz0, no electron. So, it is going to make 3 bonds only, therefore, these 3 undergoes hybridization having producing the 3 sp2 hybrid orbitals, that pz will be intact, it will be dumbbell shape and it has no electron vacant orbital, and these 3 will be mixed with s and p character. So, therefore, spherically dumbbell 3 are formed. These 3 can be written like this, 3 sides 3. With reference to this plane, the pz orbital will be like this, right. This has no electron, this is unhybridized vacant orbital, whereas these 3 will have one electron, they are undergone hybridization. Hybrid orbitals alone will decide the angles, that is 120 shape trigonal planar. So, with reference to these 3, if 3 hydrogens are allowed, 3 sides 3. So, you have a carbon with 3 sides 3 hydrogens and one orbital, this is 2pz orbital, which is vacant orbital. There is no electron, but still the concept of writing the empty orbitals we have in practice. So, if electron comes, it will be like that pz orbital on, that is hybridized orbital, which can act as an electron receiving source. So, therefore, the CH3 plus obviously called an electrophile, that means electron philic or seeking nature is there. So, the CH3, what is the bond angle between CH3 means in fact 3 sides 3 hydrogens will be there and having the trigonal planarity. So, all that wherever the carbocation comes as an intermediate leading to give the reaction later and sp3 hybridization if it is formed, we have a plane, therefore, a new group can come from this side or from the other side. If all these 3 groups are different, we are going to get a set of enantiomers which have got the mirror image relationship and a racemic mixture is going to form. In such cases, we have to emphasize this planarity of the carbocation is the main reason to get that 50-50 D and L formation of the products. However, this a methyl carbocation is to explain to have a sp2 hybridization. Similarly, if a CH3 minus a negative means one electron extra added. For this system, let us add one electron added. Added electron goes to the last one or to the first one means the electron added will be from always to the lowest one, removed from the topmost one, that is higher energy will be electron will be removed, whereas when you add it goes to the lowest energetical level. So, therefore, the system will become now 2s2, 2px1, 2py1, 2pz1. Now if you observe the bonds, how many bonds we require? 3 bonds. But these 3p, px, py, pz, if you mix up, there is no meaning for the hybridization, is a mixing of different orbitals. All p are double. If you mix again, double will come, overlapping will be less. So inevitably s will be mixed therefore, and hybrid orbitals will be 4. All are called sp3 hybrid orbitals. Each one is having the 1 orbital, but the one orbital is having 2 electrons. So let us draw all the 4 like this. 4 sides, 4 mutually. Out of this 4, any one you can choose, shows that is a paired one. Already it is paired, but it is a sp3 hybridized orbitals. sp3 hybrid orbital. The other 3 will be having 1 electron. They overlap with the hydrogens. So the expected angle between the two will be the 109 degrees. However, a theory that in the valence shell, if there is a lone pair is there, this lone pair has only one side pulling, the other side is not pulled. Imagine that there is a balloon, both the sides you are pulling, it will be like this. Whereas a balloon, only one side you are pulling will be like this. That means the length decreases and it starts bulging. So because of the reason, the same thing, the other side there is no counter force, it bulges its shape and therefore it puts a pressure over this side. The bonded pairs are 2 electrons, 2 counter forces, they will be little long shape and it will be bulged, so therefore it will put a pressure. This bond angle or the angle between 2 hybrid orbital will be less than 109 degrees 28 minutes. Definitely, as the lone pair number increases, also the angle will be decreases. However, instead of hydrogen, if the shapes of that groups like phenyl or ethyl, bigger the groups, reversely this side angle increases, the other side the angle will be decreased. Now right now the hydrogens were very small, so this side there is no hindrance, but the lone pair bulges and the 3 hydrogens will come close. This is called slightly disturbed or distorted tetrahedral. This is not tetrahedral, this is trigonal planar perfectly, because this unhybrid will not have any deviation in the shapes or the angles. But here this is going to deviate and the shapes and the angles are slightly different. If it is a hybrid orbital, regular tetrahedron in methane, CCl4 and all that. But in this case, this is something like ammonia molecule with 3 hydrogens and a lone pair, the same symmetry, isoelectric species there. So something like that. Here also we have a distorted or slightly disturbed tetrahedron having the 3 hydrogens slightly come close. As I said, the hydrogen, if it is shifted, that is changed with the bigger groups, the angle will be again increases. This is what carbanion. So this is first one is called carbocation, methyl carbocation. So the carbocations will have sp2 hybridization with a trigonal planarity, whereas carbanion, methyl carbanion will have a sp3 hybridization with a disturbed or a distorted tetrahedral shape. Whereas we have another type of the species like a CH3 dot, that is a free radical. The free radical, no loss, no gain. So the same electrons will be there in the free radical, and we have an option also. There are some, that is, evidences are there, it may undergo sp2 as well as sp3. So we have 2 types of the options. If it undergoes sp3, all will be the hybrid orbitals will be there, and 3 will be undergoing overlap with the hydrogens, 1 will be with 1 unpaired sp3 hybrid orbital. This is, if only sp2 undergoes 3 sides, 3 hybrid orbitals and trigonal planarity 1 1 1 will be overlapping with the hydrogens. And what about the other one? Means there will be a unhybrid orbital which is having the 1 electron, that is pz orbital. So, we have two types of the options are there, because we have evidences from the different reactions. Sometimes it is showing sp2 hybridization, sometimes according to its that is product formation shows that there is an evidence for the sp3 as well. So, free radicals may have sp2 and sp3, but carbocation is fixed, that is sp2 hybridization, carbanion will have the sp3 hybridization. So, this is all about the hybridization, and we too can go for the certain examples, like let us take some typical examples like CH3 CHCH3 plus. What is the angle between these two methyl groups? Now, we have written in such a way, it's a line or a linear shape, and we think it is 180 degrees, but the carbon hybridization is the criteria. Carbon with a carbocation with the 3 sigma bonds, it is sp2 hybridization with 120 degrees and trigonal planarity will be there. So, therefore, never go for the consideration of the shape what is written on the paper on the board. It is written like this, but originally the carbon will be in the center, 3 sides, 3 groups, 1 hydrogen, 2 methyls having a regular tetrahedron, regular trigonal planar, having the a carbocation that is vacant orbital acts as an electrophile. Similarly, a CH3, a minus with CH3, this carbon will have a tetrahedral shape and with a slight distorted tetrahedron, because a lone pair may have a this side, that side, and the methyl groups also may have a small distortion. Cases like CH3, H double bond CH with a plus charge on the carbon. Now, this is a carbocation, no doubt, but how many sigma bonds right now this carbocation making? Out of the double bond, 1 sigma bond, and this is 1. So, therefore, there are 2 sigma bonds it is making, means 2 sigma bonds, as you see the chart also, sp hybridization. How do you explain this one? Means there is a out of 4 electrons, 2s1, 2px1, y1, z1, 1 electron is removed. Only 3 available electrons are there, and of that 1 is making pi bond. So, hybrid orbitals are only 2, that is sp hybridization. Okay. Similarly, a CH3, a CH double bond C with H and minus charge is there. Now, here carbanions, I said it is sp3 hybridization, but here this is a carbanion having how many hybrid orbitals? 2 hybrid orbitals and a pair of electrons, just like ammonia, 3 sigma bonds with pair, it is sp3, like that here also 2 sigma bonds, 1 pair, the pair is in the, go for the hybrid electronic configuration, 2s2, 2px1, 2p y1, 2p z1. Here is a pair is there, and only 2 hybrid orbitals. 2 hybrid means the 2s and 2p x and y, this undergoes hybridization, and this will be pi bond formation. These 2 are sigma bonds, and this acts as a pair. So, 1 pair is there, 2 sigma bonds and 1 pi bond. So, hybridization will be sp2 hybridization, of which 1 will be a pair will be there. Any one you can take, 1 pair will be there, and 2 hybrid bonds, 1 with the hydrogen, 1 with this carbon. So, 1 vacant orbital is there, that is 1 single electron, this undergoes a pi bond formation with the neighboring carbon. So, therefore, it is not that all carbanions will have sp3 hybridization. How many sigma bonds? In addition to that, is there any charge? If charge is there, remove electron. If minus is there, add 1 electron. Added electron goes into the s orbital. That pair will be involving in the hybridization. Otherwise, there is no meaning for the mixing of the pp orbital. So, s and p are mixed. So, hybridization will be sp2 hybridization. Questions like acetylene, for example, it may break into the 2 types, heterolytic fission may give to the acetylene with a anion and H plus. Okay. Similarly, you too can make another chance type of breaking heterolytic fission, acetylene with plus and H minus. This is possible, quite easy, but this never takes place. Why? The reason is here, the 1 sigma bond with 1 pair, sp hybridization is possible. Here 1 sigma bond, that's all, there is no other, these 2 are pi bonds, there is a loss of electron. 1 sigma bond means only s orbital, there is no hybridization that leads to the instability. So, this type of the acetylene with plus never forms at all, that collapses because of the instability or no hybridization, only 1 sigma bond, that is right, only 1 sigma means no hybridization. So, there is no possibility of this type of the acetylide carbocation will not be formed, but acetylide anion will be readily formed. sp hybridization is quite a possible one. So, given molecule you have to observe how many sigma bonds, that is the result of the hybridization. However, also consider, is there any lone pair is there that is also involved in hybridization? Is there any positive charge, that is electron is removed? So, what type of the consequence will be there? We have to understand.